Okay, I think you are hearing me. Okay, so we will start. I think that the rest of the guys will show up. Probably they are still solving yesterday's problems. Because I see you guys, you are solving them yesterday evening, and even today in the morning I saw some submissions. So it's very good, I like it, that you are trying really hard. Okay, so we start today's lecture with the solutions to solve problems from the yesterday's contest. So these tasks were pretty challenging. Even the tasks that were supposed to be easier ones, they had some twists in it. So it was not very easy to like get the accepted from the first try. So even if in those easier tasks there were some tricks. Okay, so we will start from the task B and A. Okay, in the task we had a string up to on the alphabet up to 4 letters, but it really doesn't matter that there are 4 letters. Actually, there were 2 kinds of letters, so we'll just call them A and B. Okay, and for each substring of the string, we could define some kind of measure, and it was as follows: if there were no b's in the substring, so I can just write the number of b's. If number of b's is 0, then let's call the weight of the substring is equal to 0. Otherwise, the weight of the substring was equal to number of a's in the substring divided by number of b's. And we are supposed to find the substring which will give us the highest possible value. It looked like. Turned off automatically, so probably the battery. Okay, so how to do this? So first of all, we have 2 special cases. If we have a string which has only a's or only b's, then the weight of the string is equal to 0. So if we have A, if our input is all of A's or all of B's, then the answer is the whole string. Because there was one thing to note. So from all of the strings which have the highest value, we have to return the string which is the longest. So if our input is all of A's or all of B's, then every
substring has weight 0. So we just have to return the whole string. So let's assume that we have at least one A and at least one B in the input. So which string has a big value? So we have to have like many A's in the string and not many B's. So let's assume that if we have one B, then probably it will be the best string which can be. So we can just because if we have one B and A's, we have the value of N. So how to prove it? So let's suppose that we have our optimal string has some A's.
Is it on? Okay. So let's assume that our optimal string has some A's and has some has at least 2 B's. Then we can partition this string. Let's suppose that in such a way that each part will contain only 1 B. And it's easy to see that at least one of the parts will have the value as big as the value of the whole string. So we can, instead of taking this optimal string, we can just take the one of the parts. So in our algorithm, we can just look through all the b's in our string and just calculate how long are the substring which contains only 1 b. So it's easy to just first go through all the letters and calculate the length of all the blocks between letters B. So, for instance, if we have this string, so the blocks are as follows. Here we have only 1 A. Here we have a block of 0 A's between 2 B's. Here we have a block of 3 A's, and at the end we have a block of 0 A's. And so we just so our optimal string will be we have to find the maximum of sum of 2 consecutive values in this array. Okay, so that will give us the string with the highest value, but not necessarily the longest string. So this is another catch in this problem, because we said, okay, so we have to only consider strings with 1 B, but to get the maximum value. But actually, there is an example when we can get a longer string with the same value. So in this example, the maximum value is equal to 1, and is achieved for 2 strings. But actually, the value of 1 is also achieved by the whole string. So this string contains 2 letter B's, not 1. So we have to also consider the case when we have 2 letter B's, and it's quite easy to see what are the form of such strings. So these strings have some letters A, then letter B, again letter B, and some more letters A. So we are only interested in strings of this form. So again, it can be easily we can iterate through all this kind of strings using our array, because then in our array we have to have first a block of KAs, then block of 0As, and another block of KAs. So I saw them, some of the teams got this part right, but didn't see that we also have to consider cases with two-letter release. Okay, so that was task E. So if there are any questions, you can just ask me. And if not, we will go to another task. So we will try with ascending paths. Okay, in this task we had a graph. So we have some nodes in the graph, we have some edges, and the edges in the graph have weights. Okay, and our task, it could be like multiple edges. And our task in this was to find a walk in a graph in such a way that we can visit one vertex multiple times, but every edge which we are visiting must have greater weight than the edge we were visiting before. So, for instance, if we can start from any vertex. So we can start, for instance, from this vertex. Maybe I will use color. So we can start from this vertex, go through edge with weight 2. This edge does not have weight, so it will be 3. We can go through this edge of weight 3. We cannot go with this edge because it has only weight 3. We can go with this edge, and then we can go with this edge. And if this one has weight 7, we can go also with this one. So our longest path has 1, 2, 3, 4, 5 edges. Right. And the graph was the number of vertices and the number of edges was around like 200,000. So one of the solutions I saw some people send was, okay, so let's try to just simulate this path. So let's start in one vertex and just go make a traversal of the graph using only the good edges. So the edges which have greater weight than before edges. So of course, if we do this completely naively, then we will exceed time limit. So the solution was like we will remember some of our previously taken paths. So if we are what information we will have to remember. So if we are starting in one vertex, then in order to know which edge we can go or not, we need to know the weight of the previous edge. So we can just write the recursive formula, which will take the number of the vertex and the weight of the previous edge. And then in this formula we will just try all the edges which have the bigger weight, and we just and we will try all of them. And we will just memorize the values we calculate. So what's the problem with this solution? Well, the problem is it's still too slow. So we can have. So let's assume that we have this kind of graph, that we have multiple edges of different weights which go to one vertex, and from this vertex we have again many edges of let's say another many weights. So in this algorithm we will start our walk in every vertex. And from every vertex we will go through the path with different weights. So we will end in this vertex. So let's call it V. We will end with this vertex with every possible weight from this side. And then during the execution of this vertex, we will try to go through all of these edges. And all of these edges has weights. Well, it doesn't even matter what weights do they have. We will just see through all of them to see whether they are greater or smaller than these numbers. So if here we have like m half edges, and here we have m half edges. So in this graph we will need to do at least. At least m squared operations to just go this part right, and it will definitely time out. Okay, so this is not the way to go in this task. So let's try not to construct the path in this way. Let's try with the edge of the smaller size. Okay. Firstly, assume that all of the edges have different weights, because this will simplify a little bit our problem. So let's say that this one is 60. So let's remove the edge with the smallest value from the graph. So let's remove this one, and let's assume that we just calculated the whole thing for the smaller graph. So what do we want to know for every vertex? We would like to know for each vertex the longest path. The length of the longest path which starts in this vertex. Okay. So let's assume we have all of this information for the smaller graph, and then let's reintroduce the edge of smallest weight. So how does this edge can help us? So first of all, if we want to use this edge, we have to use this as the first edge in the path, because this is the edge of the smallest weight in the graph. So if we want to use this edge, we will start either in this vertex. Let's call it V, either in this vertex or in this vertex. And then we will go using the longest path which starts in them. So either we start in V, go with edge of length 1 and go with the longest path in U, or we start in U, go with this edge and go with the longest path in V. So we can just update the longest paths which starts in V and which starts in U. So the longest part which starts in V is either the longest part which starts without the edge of length 1, or it's edge of weight 1 plus the longest part which starts in U. And similarly for the vertex U, we will have to do this update. But of course we have to be careful, because both these updates we have to do in parallel. Yes, because if we change the weight or the longest path for V here, we do not want to. We still want to have the odd value. So these are in. These have to be done in parallel. Okay, so what is the time complexity of the solution? So because we now add the length, the smallest edge, but of course we can just iterate this process to add the edges of the weight in order of their weights. So first of all, we have to sort all of the edges, which will get us the time m log n. And then we will just iterate through all the edges, yeah, and we will have to update all of the, every time we will update only 2 values. But we have to initialize the array for this array for all the nodes, so we just plus n. Okay, but this is the solution with the assumption that all of the weights in the graph are distinct. So this would not work if we will have more than one edge with the same weight. Because, so for instance, if we have 3 here and 3 here, so here we had an assumption that if we add the edge 3, the longest path which starts in these vertices use the edges which have weight greater than 3. And if we start adding edges with value 3 one by one, then probably we would get the path which contains more than one tree. So again, we will do this kinda in parallel. So we will try to update all of the edges with the same weight at the same time. So how to do this? So again, we just sort the edges, and then we will update them in blocks of containing the edges of the same size. So instead of directly updating our array, we will just postpone the update until the block of edges of the same weights finishes. So instead of just making the update, we will have an array which will hold all the updates for us. So let's call the array so let it be a vector, and in the vector we will just put a pair, and this pair will contain two things. First, the number of vertex we would like to update, and the value which we'll be updating the vertex with. So for the first update, it will be this. So also for vertex U, we will have the similar update. So we are just storing these updates in the array, and after we consider all the edges with the same weight, we will just make these updates. So we will iterate through. So let's write it in pseudocode. Let's iterate through all the vertices and the value in the vector, and we just update the vertex. So we could write the value, the new value of the vertex is the value which comes from the updates. And I saw some solutions which did this, and it's not entirely correct, because what we have here, we just updated this value, but remember that we could have more than one update which considers the same vertex. And we would like to take the maximum value of all these updates. So if we just write this in this form, then we will only take the value which was the latest in all the updates, and not necessarily the value which was the greatest. So we need to put another max here, and we need to take only update if the new value is greater than the actual value of the vertex. Okay, so this is the solution. It runs in the same time because we just for each update we will have a constant time. We just put the update in the vector and then just perform that. Okay, so again, it was not very difficult question, but it has some twist in it, which makes it a little more tricky. Okay, so these were, I think, two the most easy tasks from the set, and so which task you would like to hear now about? Because then we had three more tasks which were solved by some teams. We had Wombat, we had QR codes, and maximum slice. So which one? Sorry? Okay, so I heard some whispers about maximum slice, so let's go with it. Okay. So you probably know the standard version of this task when you are giving an array of numbers, and you are asked to calculate the slice or the part of the fragment of the array which has the maximum sum. And of course, in the array there could be numbers with which are negative, because otherwise the whole array would have the maximum sum. So again, so in this. So let's recall how to solve this problem. So we just adding the numbers one by one, and we will have two variables. The variable sum, which will have the current maximum sum, and the value max sum, which will hold the global found maximal sum. So so we are adding elements one by one. So first of all, we just add the element to the sum, and if AI is positive, then definitely it's good to add it because it will increase the current sum. But if it's negative, it could decrease the current sum. So as long as sum will remain positive, maybe it's good to get this negative value because it will allow us to get some more positive values in the future. But if this negative value is so low that it will bring the sum below 0, then it's not. Then the whole prefix which we will just get could be discarded, because we can easily start with the empty slice. It will have the bigger sum than the slice with the negative sum. So if we get that sum is below 0, we just reset it to 0. And every time we add one element, we will update the maximum sum. So we will just remember what already achieved maximal sum is. Okay, and at the end of this algorithm, we will get in the very maximal sum, we will get the value of the answer to the question. So we can also look at this problem in a graphical way. So let's make a graph in which for every value we either go up if this value is positive, or we go down if this value is negative. So we are starting from from 0, and every time we go up. So here we will have the value of the current sum. So every time we go up, it's okay. If we go down, but we do not go below 0, it's still okay. But if we go below 0, then it's good to start again from this value. So again, we will just put 0 here, and perhaps we will go up, perhaps we will go down again, and then we will start with 0 again. So this is the graphical way to see this algorithm. Okay, but our task was a little bit harder. So we want to again calculate the slice of maximal sum, but we are allowed to make one swap in the array before that. So we can just take two indices in this array and just swap them, and it showed that this can result in the slice of bigger value. So for instance, if we have like 10 minus 100, 1. So we see that that if we swap this -1 with this 10, we will get 10 here, and we will just can take this whole thing as a slice of maximum value. So the slice without swapping, the answer would be 10, but with swapping the answer would be 15. Okay, so why would we need to swap? If we want to swap a number, this means that we want to swap it inside the maximum slice. So we only benefit if we swap in some way that it will incorporate to the value of the maximum sum. So let's make a picture, and let's assume that we want to swap some element here. Let's call it in the index I, and we want to swap some element from some other part of the array here. So let's assume that it will result in the maximum slice, which is as big as that. And even if we don't know which element will go there, we know that the slices which are before this element and after this element, which have to be as which have sum as bigger as possible. So actually we want here have a maximum left slice of element I and the maximum right slice of element I. And we can calculate them, because let's remember this algorithm. So what actually we are calculating here? So this value sum is always has always the biggest possible maximum left slice of element I. Yes. So if we are going through the array, we always remembering the slice which has maximum value and ends in element I. So actually, to calculate the maximum left slice for all of the elements, we just use this algorithm, and we will. And here we can just perhaps. Here we can just write that maximum left slice. No. Maximum left slice of element I is the current sum. So before we update with the element I. Okay, and to calculate the maximum right slices, we can just do it by reversing the string and do the same algorithm, or just without reversing, just going in the other direction. Okay, so now it comes the part which element should go here. So we can have two cases. Either this element is outside of this slice we have just calculated, or it's inside this slice. So the first case, when this element is outside of the slice, it's slightly easier. So let's assume that the element we would like to swap this guy is here. So it's outside of the slice. So which element should it be? Yeah, it should be a maximum element which is outside the slice. Yeah, because we can use any of these elements, and they don't change these two parts. So we can just take this element which is of maximum value. So to do it fast, we would like to know what is the max element in this prefix, and what is the max element in the suffix. So we can just call it max element pref. And here we would have like the number L and max element right suffix. And here we have like the number. And L and R are just indices, which form the slice of maximum sum. So let's observe that we can also calculate these indices with this algorithm, because every time so when this indices changes, only when we are making the sum, only when we reinitiate the sum with 0. So if we reinitiate it, then the maximum, then the start of the maximum slice goes to value I, and if we do not reinitiate it, then the start of the slice is the same as before. So we can also not only we can have the array which tells us what's the size of the maximum slice, but also what is the starting index. And using these starting indexes, we can just take the maximum the prefix. Maximum of the prefix is easily calculated by just like prefix sums actually. But we are not adding the elements, but taking the maximum with what we had before. Okay, so this is the easy case, and we also had the slightly harder case, because it turned out that it could be good for us to swap the element with element I, to swap the element which is inside one of these two parts. So for instance, let me show an example. Okay, so let's assume that our element I is here, it's this 0. And so maximum left slice, it only takes 2. And what is the maximal right slice? So actually the maximal right slice is the whole string here. It has because this is good, then this 4 is bigger than -2, and this 2 is bigger than -4. So the whole part is the maximum right slice. But actually we can do better by swapping this 0 with the element 4. So if we swap these two elements, here we will get 0, and actually this whole part could be discarded, because as you can see, this part will have the value of -3 plus 2, so this part will be negative. So actually if we discard it, it will give us the bigger sum. So the answer would be, if you want to swap something with 0, then the answer would be to swap 4, and then then the maximum slice will contain 2, 4, and these 2 5s. Okay. So
we have two questions. First of all, which element we would like to swap this guy with, and after swapping, how much we can gain. Yes. So what is the the largest negative thing we can get rid of? Okay, so we can rephrase it in some other words. Basically, we can. So if we have this maximum right slice, we want to know what is the minimum value of some suffix of this slice, which results which comes after changing one of the elements in this slice to 0. So why is it so? Okay, because for the answer we would hold the maximum right slice, and then we want to change to swap one element from the slice with 0. So actually we can not make a swap, but we can change this element to 0 here and put it here. So actually we do not have to change it with any element here. We can just assume as we are swapping it with 0. Because if this element is negative and we make a swap, so it probably won't do as good to take this negative element here after all. So we can just assume that we are swapping with 0 as in this example. So what we want to do is to calculate what is the minimum suffix of this max right slice after changing some element with 0. So in this case, the optimal thing is to change 4 to 0 and to have this suffix of the minimum value. And so actually how to calculate this for all of the slices. Yeah. So again, we will use this. Use this algorithm, and we will. So every time we reinitiating sum to 0, then the length of our maximum right slice is equal to 0. So we don't have any element which we can swap. So the interesting part is what if we are adding a new element. So let's assume that we have this maximum right slice, and we already calculated that the prefix which has a minimum value after swapping some element after changing some element to 0, and we are adding a new element here, and we are adding it in a fashion that we are extending the maximum right slice. So either this value is still optimal, or it's more optimal to discard all of this thing and now we want to change some element in this slice to 0. So again, which element we should take? So we should take the maximum element, because if we change the maximum element to 0, then this slice we will take the minimum value possible. So again, it's just taking either this guy or this guy without the maximum element in the whole slice. And again, it can be done using this algorithm. Yeah. So that concludes this algorithm. What is the time complexity? So we have different arrays here, but most of them we're just calculating using this algorithm, and this algorithm is clearly works in linear time. Yeah. So that was not super easy, but it was doable, and some of the teams actually solved this problem with the competition. Okay. So 3 problems. We have 3 problems. So which one to attack now? So let's try QR codes, okay? Because this was also the problem which some teams solved during the competition. Okay, so in this problem we had a rectangle, and this rectangle was divided into small squares, and each of the squares can be black or white. So let's assume that we have this. Something like that. And our task was to calculate the sum of area of all subrectangles which have the same color. So for instance, in this, if we want to calculate all the rectangles which were white, the sum of area of all these rectangles, we would do as follows here. Here we have 1, 2, 3, 4, 5, 6, 7 of rectangles which are 1 by 1, so their area is 1, and we have 2 more of them which are 1 by 2, so the area is 2. So this is the area of all the white rectangles, and the area of the black rectangles is it's bigger. So for instance, we have to calculate this guy and all of the smaller guys and this one, and we do not want to calculate this guy more than once and again. Sorry. So first observation is that we can do white rectangles and black rectangles separately. So we can just calculate the white rectangles and then swap all the colors in the array and do the same algorithm for the second time to get the upper color. So let's assume that we want to calculate all the black rectangles. And so probably you saw some of the similar problems in which you have this kind of grid, and you have to find a rectangle which is formed from squares of the same color, and it has some property. For instance, it can be a rectangle which has the maximum area, or the maximum perimeter, or something like that. So all of these tasks can be solved using the same technique, and this task is not an exception. So in this technique, we want to separately consider all the rectangles which have the, let's say, lower left vertex in the same cell. So, for instance, let's consider this point, and let's consider all the rectangles which have the lower right vertex here. So, for instance, this rectangle is right, and all of the rectangles which are contained in it. Also, this rectangle is right, and this one. Okay, so as you can see, all of the rectangles which are like fixed in this point are contained in the big rectangles which make some kind of a staircase here. Actually, this staircase is sufficient for us to calculate all these rectangles which are fixed here. And the idea of this algorithm is to make use of this staircase to calculate the rectangles which are fixed in the next point. So maybe this example is not quite good. So let's change it a little bit. So let's assume that here we have white things, and here we have. So let's assume here we have one. So if we have this staircase for this point, so how this staircase changes when we go 1 point to the right? So let me take another color. So the tallest rectangle here would be this one, and actually this So this is the tallest one, but all of the smaller ones are still represented in this smaller staircase. Yes, because here we can just extend this guy here, and it will be still good, and we can extend this guy here, and it will be still good. And we can got this staircase. So, in order to manipulate the staircase, we will use the stack. And on the stack, we will have all these rectangles. So, for instance, stack for the first guy would look like this. We have this guy of size 2 and 2. Then we have another one of size 3, 1, and we have another one of size 4 and 2. And then we want to update it using this column. So, what we are interested in is the height of this column. So this column has height 4. It has four black cells above this point, and actually we can calculate all of these heights for all of these points using the dynamic programming in the time n squared. So we can assume that we have the array with all of these heights.
Wait, that is 5-2?
Yeah, correct. It's 5-2. So I'm standing too close to the to the blackboard. Yeah, you're perfectly correct. It's 5-2. Yeah, and now it's we have the height 4. So we want to update this guy. But what we are seeing that in our stack, all of the staircase must be formed of rectangles of greater heights. Yes, because if this has height 4, so the height of all of the rectangles which are fixed here will be no more than 4. So actually, no rectangle could get this cells. So what we do is we just pop the last thing from the stack. We actually pop it in a while function. So as long as the last thing on the stack has greater height than the next than this column, then we just pop it, and we actually merge them into one rectangle. So we merge them in one rectangle, which will have now size 4 times 3. Okay, so we update this stack. So what is the time complexity of updating this stack? So every time we go, we either add one new column, or we pop some elements from the stack and then add one column. But as you can see, every time, if you want to pop something from the stack, it has to be pushed to the stack before. So actually, all of these things takes the manipulating on the stack takes the total linear time. If we are looking at all of the points which are in the same row. So we have linear time for one row, and we can just do all of these rows separately, and we have n rows. So we will get the total time of manipulating the stack would get us time n squared. Okay, so that is the part which is common in all problems which in this form. But actually, now we need to see what additional values we want to store in this stack in order to calculate the sum of areas we are interested in. And in my solution, I store four values. So first of all, we store these two values. So we store the height of the element on the stack and the width of this element. And also we will store the sum of heights. The sum of heights of all the rectangles which are fixed in the lower right vertex of these rectangles on the stack. So, for instance, for this guy, it will be the sum of heights of all the rectangles which are inside this guy and which are inside this and this. And again for this one and for this one. And the last thing, we will store the the thing we are interested mostly with, the sum of areas. So we will sort the sum of areas of all the rectangles fixed in this points. So if we manage to calculate this, then it's just a matter of summing all the PIs through all of these points in the through all the points. So let's see how to actually calculate these things. So we saw how to calculate the HI and WI, the sizes of the rectangles. It's not very hard. So let's assume that we are interested in the first rectangle in the stock. So what is the sum of heights and what is the sum of areas for this rectangle? So if this rectangle has height h and so all of the rectangles which are fixed here have this form. So they have height at most hi and width at most wi. So what is the sum of areas for these rectangles? So every rectangle has width of from 1 to wi. So it's just. So these are all of the wider rectangles, and they have the height from 1 to hi. So it's just using binomial coefficient. It's just that. And sum of the heights is even easier because for every rectangle which of different widths we only are considering it only in height of these rectangles. So we have wi of rectangles of each height. So it's wi times the binomial coefficient. So this is for the first element in the stock. Okay. So now we need a recurrence formula. Okay. So for recurrence formula, we will use the values from the previous rectangle. Okay. So let's assume that here's the last one, and what values we will be using. Yeah, and let's suppose that here we have we calculated for this guy these two values. So what are the heights? So first of all, if we are considering the rectangles which are fixed in this point, so we have two possibilities. Either this rectangle is fully inside this ith rectangle, or it's not fully inside. So in this case, it should go here or here. So for these rectangles which are inside, we can just rewrite the above formula. And what do we do with these rectangles which are not fully inside? So let's see that here's the one-of-one correspondence with these rectangles and with these rectangles which are fixed in this point. So if we just cut every this rectangle using this line, we will get another rectangle which is fixed in this point. So here, and these rectangles have the same weights, so we can just add all the weights for these rectangles. Okay, so what about the areas? So areas get a little more trickier. So again, the areas for the rectangles which are fully inside, it's just the same formula. But now we are interested in these rectangles which are not fully inside this one. So again, we have one-to-one correspondence, but the areas of rectangles fixed in these points are somewhat bigger. Yes, because the area of this guy is this area, and we have to add Wi times the height of this new guy. So again, we can add pi minus 1 for all these pink areas here. And then we have to add another term for these additional parts of these rectangles. So all of these rectangles have the same width. So the width is pretty easy. But what are the heights of these rectangles? So actually we calculate them. Yes, because we have this value which says what is the total height of all of the rectangles which are here, and it's sufficient because for us, because all of these rectangles here have the same width, so it doesn't matter from which rectangle which height comes from in the sum. So we can just multiply this by the sum of the heights. Okay, yeah. So as we can see, every time we add new column to the stack, we will have to update these four values here. And as you can see, we can just do it in the constant time. It's not big math here. So overall, the algorithm will run in time n squared. So because the input is n squared, it's clearly the optimal time. So that would be for QR codes. And from the yesterday's tasks, there was one more task which was solved during the contest. It was the task Wombat. It was solved by one team and only 10 minutes before the end of the contest. So that was pretty amazing. And it was actually the only submit for this task during the whole contest. So congratulations. And so yeah, I think we can use this board. Okay, so there was some interesting story about wombats in the task statement, but apart from the story, what we have to do is quite simple. We have a number n, and we want to find the polygon with sides which are parallel to the axis of the coordinate system, and all of the sides of this polygon should have integer lengths, and all of the sides should have different lengths. So there was an example in the task statement which showed what is this polygon for n equal to 6, and let me just write it. Okay, so for n equal to 6, we have this rectangle, and it has sides of length 1, 2, here we have 3, here we have 4, here we have 5, and here we have 7. And we are asked to find such a rectangle for different ends, find such a polygons for different ends, and with one additional requirement that the perimeter of such a polygon should be as small as possible. So we have actually two questions. So first of all, what is the minimal perimeter for a polygon? And the second question, how to construct the polygon with the minimal perimeter. So as we can see, so we can just try some simple examples. First, two obvious observations is, first of all, n should be even, because otherwise we cannot construct any polygon. And it must be at least 6. Because if n is equal to 4, then we have to construct a rectangle, and rectangle, of course, has sides with at least 2 sides with the same length. So 6 is the minimal example, and we could be tempted to try to construct the polygon with the really minimal possible perimeter. So to just use the sides of lengths 1, 2, 3, and up to n. And as we can see from the example, it's not possible here. Here we have 1, 2, 3, 4, 5, and not 6, but 7. So the question is why? So actually, for this, we can see why it's not possible to use 6, because we have the sum of the perimeter. So let's call it P. The perimeter of this rectangle, if we use all of these values, is 1 plus 2 plus n. So it's 1 plus n times 2. So n is obviously even. So this guy is equal to
21.
Sorry?
21.
Yeah, okay. Yeah, but I'm trying to get the general case. So this parameter is of course an integer, but let's take a look at But let's take a look at these edges which are on the left and on the right. So if we are starting from this vertex and we are go up, then we have to like go down the same amount. And if we go right, then we have to go left the same amount. So actually the perimeter of the rectangle must be divisible by 2. So actually this number should be divisible by 2. N is even, so this guy 1 plus n is odd. So actually to get this, n must be divisible by 4. So if we want to have at least a chance to get this, then n must be n must be divisible by 4. So 6 is not divisible by 4, so we cannot get 1, 2 through the n. But it turned out that in these cases we can find the perimeter which is a little bit bigger. So we know that we couldn't possibly get this perimeter, but we can get a little bigger. So we can get p plus 1 if n is not divisible by 4. So okay, so actually if we produce the algorithm which gives us these parameters in these two cases, then we know they are optimal, because clearly we couldn't get better. But the thing is, well, first of all, it's not obvious that we actually can get to this minimum, but we'll show the algorithm which really get this minimum. Okay, so first of all, we see that we probably will have to do some cases here. So here we have two cases, if n is divisible by 4 or not. And actually in the algorithm I will present, we have 4 cases, which also includes whether n is divisible by, what is the remainder of dividing n by 8. So let's start with a simple example when n is equal to 8. And let's see what we can do here. So I probably will use this blackboard because I want to draw some additional pictures. Okay. Okay, I think I got it right. So here's an example which shows the minimal parameter for n equal to 8. So we will use this example to actually construct the optimal parameters for in the case where n is divisible by 8. So what can we see here is we can we divided our edges into two groups of each having 4 edges and edges of consecutive size. So in this, so we have actually 2 parts in our polygon. So the one part contains all of the edges of sizes 1, 2, 3, 4, and the other part contains all of the other edges. So actually, we can do a little more general thing here. We can forget about these numbers, and we just can assume that they're slightly more general. So instead of having like edges of length 5, 6, 7, 8, we can just have like 4 edges of consecutive lengths, and then we can construct this kind of the almost a rectangle with this thing here, which can be used to like glue another part of the polygon here. So in other words, we created 2 parts which can be glued together, and both of these parts are the ending parts of the polygon. So now we would like, if we had a part which starts from this kind of opening and ends with this kind of opening and has 4 sides of the consecutive lengths, then we can just use this guy and glue them together to get the bigger and bigger polygons. So the question is, why is not possible? Yeah. So this guy and this guy has the same length, and this guy also has the same length. So idea is, let's try to generalize this a little bit more. Okay, but we can do such a thing. So we have here edges of 4 edges of consecutive lengths, and we make some kind of gadget which has the opening of, let's call it opening of size 1, which is the same as this one, and it has an opening of size 2. So with these gadgets, actually we can construct any polygon for n divisible by 8. So how do we do this? We just partition all the lengths into groups of 4, into groups of 4 edges of consecutive sides. We start with this gadget. So we start with, let's call it gadget 0, 0, 1, because it has no opening here and opening of 1 here. So, and this gadget is 1, 2. So we can just start with gadget 0, 1. Then we can go with gadget 1, 2. and back with gadget to 1. And actually, we can just repeat this part as many times as we want, and then we will finish with the gadget 1, 0. And the length of this string is equal to, well, it's even. Each gadget takes 4 edges. So this shows us how to construct all the polygons for when n is divisible by 8. Is it clear for now? So we clearly see that this polygon, no edges of this polygon will intersect with each other, because all of the gadgets we're just stacking them one on top of the other. And having this in mind, it's just a matter of getting some more gadgets to work with when n is not divisible by 8. So, for instance, if the remainder of, so this is the case when the remainder is equal to 0. Another case is what if remainder is equal to 4. Then we would like to have one more gadget, which comes from 2 to 0. So and this is minus 2. Okay, so this gadget, it comes from 2 to 0, and we can use it here. So once again, we just use all the gadgets we have here, and instead of getting from 1 directly to 0, we go from 1 to 2 once again, and then we go from 2 to 0. And this has this has odd length and times by 4, so this is it. And now we have to consider cases when n is not divisible by 4. So actually we have to construct a gadget which takes 6 edges, and actually it's important which edges it takes, because let us see that we will have many groups. The smallest edges we will contain groups with edges of consecutive lengths, but the last edges, for instance n minus 1 and n plus 1, are not consecutive. So we will just construct a gadget which takes the 6 of the last edges. Okay, so actually no. So no. So in my so I'm seeing that my notes in my solution is slightly more complicated. So yeah, so perhaps there is a solution like that, but we can go with another one. Okay, so we construct actually. No, we can extract one gadget, but it's okay. Let's try to do this. Okay, so here we will have a different opening. So what we did here, we took the we actually took the first 6 of the edges of consecutive lengths 1, 2, 3, 4, 5, 6, and we constructed the gadget which, and we can call it like 0, 1 prim, because it has no opening here. And it has opening of, let's call it a bigger one, of size big one. And so yeah, so this kind of opening, this guy is of size 1, 1, and this is of size 1, 2. So actually we can take this guy and make it, instead of this kind of opening, to make the opening of size 1, 2, and instead of this kind of opening, we can make an opening of size 2 times 3. So we're just shifting these two sides by 1 to the right. So thanks to that, we can get a gadget which opening big 1 and big 2. Okay, and finally we can take this gadget and make it create here a big opening of big 2, and now it will have edges of n-3, n-2, n-1, and n+1. Okay, so this gadget will have the 4 of the longest edges when n is not divisible by 4. And okay, so these are all the gadgets we need. So if n is divisible, remainder is 2. Then what can we do? So we are starting from the 0, 1 prime. Then we got to 1 prime, 2 prime, 2 prime, 1 prime, and we can take it as long as we want. And then we are finishing with the we're finishing with 1, 2. 1, 0. Yeah. So actually, we can also finish with 1 prime, 1 prime 0. So this is this guy, and we see that we can just. So if we have opening which is a little bit, actually here we have a little bit taller. Then we can make this edge to be n+1. So actually, if we have an opening which is a little bit wider, this guy should be like a bit flipped, and it will be okay. All right, and if in the last final case when we have the remainder of 6, we can just take 0, 1 prime, and again, as long as we want 1 prime, 2 prime, 2 prime, 1 prime, and finally, once again, 1 prime, 2 prime, and 2 prime 0, and 2 prime 0 is here. Okay, so that looks like we did it. Yeah, we have all the gadgets we use, and yeah, we construct the thing for all of the others. Okay, so in this task, the hardest part was to actually convince ourselves that we can get this small parameter, and then to carefully design all these gadgets. It's not the only the only way to solve this task. You can just create different kind of gadgets as long as they work. And as for the coding part, it's not very hard. Well, actually, we have. I think it's the easiest way is just to make these 4 cases separately, but the gadgets are small and they're repetitive, so it's not very much code. Okay. So that would be for 5 tasks which were solved during the contest, and we have a little bit of time for at least one more task, and then I will give you some hints for the other 2. Okay, so I will remove this. So another task which was tried by some of the teams during the contest, but unfortunately not with a success, was the Funfair task. Okay, so the Funfair task, it actually should have been easy, because it's talked about things we are talking about on the previous lecture. Because in the task we have two strings or arrays, and we want to calculate the longest common subsequence in these two strings. So let me just rewrite the example from the task statement. Okay, so if this task asks only for the length of the longest common subsequence, it would be easy, because here we see that the length is equal to 3. But this task asks for another thing. What is how many different substrings actually we can get? So we are told we are talking about in yesterday's lectures that we can get another things to calculate, and actually this thing is the number of optimal solutions. And so here we have a couple of optimal solutions. Actually, we have four of them. So one possible solution is to get 1, and then 2, and then 1. So we get 1, 2, 1. But of course we can take any one we want from this guy. So this common subsequence can be also can be a result from not erasing this one, but to erase this one. But in the task statement we have to calculate this guy only once. And the second possibility is to take 1, 3, and 1, and here, well, you can just take this one, 3, and this one. So the second possibility is 1, 3, 1. So in this example, we have two different common subsequences of the maximal length. Okay. So we are talking about dynamic programming, so it's not very surprising that this task also can be solved using the dynamic programming. So actually what we will need, we will actually have to calculate also the length of the optimal solution. So let's just fast recall. So we have two loops, and in each loop we are we are considering two cases. Either the last letters of the prefixes are the same or not. So let's call the L, it will be the length of the optimal solution. So if these letters are the same, so the length, we are just we are just extending the optimal solution from the smaller prefixes by 1. And we have the second case. If these letters are not the same, then we have to take the maximum. Okay, so this is the length of the optimal solution. So what about the actual number of solutions? So again, we will do this in two cases. First of all, in the case when the letters are the same, and the second case where they are not the same. So this case is a little bit easier. Actually, it's more easier. So if we have some, if the last letter is the same, then it must be in the longest common subsequence. Yes, we have no other possibility. So for instance, if we are here, so we are calculating the thing for the whole string. So we know that the last letter must be in the optimal solution. So actually, all of the possible solutions will have 1 at the end. And what will they have before 1? Well, before 1, we will have some possible solution for the smaller prefixes. And actually, we have one-to-one correspondence here. Yes, for every possible solution we can get here, we can just add 1 to get a solution for bigger prefixes and vice versa. So actually, let's write D for the array when we start our answer. So Dij is actually the same as the I-1, J-1. Because of this one-to-one correspondence. So that was the easy case. So what about the harder one? So here we have two prefixes, and they are ending in different numbers or different letters. So now we know that only one of this letter can be can be in the optimal solution, meaning that, well, either the optimal solution ends in one of these letters or it ends in some other letter. So what about the solutions which ends in A? So what is the number of solutions which ends in A? So actually all of these solutions must, they don't have B at the end, so we can just get rid of the B, and all of the solutions which ends with A will be also included in this smaller prefixes. So we can just say that, okay, so let's write all of these smaller solutions. Let's take all of the smaller solutions, and some of them will end in A, some of them will end in some other letter, but every okay, we'll come to this again once again. So the similar argument will be with solutions which end with B. All of the solutions which end in B are contained in the smaller prefix. So we can just add all the solutions which ends in B. Okay, but as we were saying, there are some solutions possibly that do not end with A or do not end with B. So maybe if we have an example. Oh, okay. So the most easy example would be like we have like C A and C B. Yes. So actually, the only solution is CC, and it does not end in A. It does not end in B. And the problem is, so did we like take the CC into consideration here? Actually, yes, because the answer CC is contained both in this one and both in this one. So actually, we calculated CC twice. So we can just remove all the solutions which we calculated twice, and all of the solutions must be contained here. So again, we use the inclusion-exclusion principle here. And is it right? Well, actually, no. So we are forgetting about one thing here. We are forgetting about the length of these solutions. So for instance, let's consider this case. So if we are to calculate, so let's see what our algorithm calculates here. So it tries to calculate all the solutions which are without the letter B. So here the longest common subsequence is CA. And there's only one of this, so in our algorithm we will calculate one. And this example is symmetrical, so we actually calculate also one for the CB solution. And then we want to get rid of all of the solutions which were calculated twice. Yes, so these solutions which supposed not to end with A and B. And unfortunately, if here the longest common thing is C, just C. So we will just so we will remove one C. But the thing is, we didn't actually calculate this C before. Yes, because it has it's shorter. So actually, it was not included in this guy and in this guy. So what we do, what we have to do, is to take the length of the longest thing into considerations, because these guys are supposed to give us the number of the longest common subsequences, but the longest common subsequences do not necessarily have to be as long as Lij. So we only want to add them or subtract them if they are of the same length. So if we can just multiply every guy here by the 0 or 1, depending on whether the length of the optimal solution here is equal to this length. So we just multiplying by 0 or 1. And again, here we also have to do this. And again, here also. Okay, so in this example, both CA and CB are of size of length 2, so they are optimal, but C is of length 1, so it won't be optimal. So here we will multiply it by 0, so the answer would be 2, and it's the correct answer for this case. Okay, so actually that's it, and so in terms of coding, this is not very serious task, but to get these numbers right, it's you have to it's not very obvious. Actually, for the first time when you see this task, it's not very obvious that you really that you don't need to store all the different possibilities here, because the thing is, you want to get rid of one common subsequence could be get in several different ways. So, for instance, if we have here more ones, then each of the one can correspond to the subsequence, and it's not very easy to see that actually that you don't have to store all the possibilities you can get to get rid of the things which were repeating themselves. So yeah, so it takes a little while to be confident with that this actually works. And what is the time complexity? Well, it's quadratic. Because for each cell we use only the constant time to update it. And one thing it should be noted here, that the thing we were talking about yesterday, the memory. So the N was around 10,000. So if we do not have enough memory to store all the arrays at the same time, because even we have 256 megabytes, but it's still not enough. So we will have to use the trick with storing only two rows of the array. And as we can see, we for calculating ij, you only use indices I minus 1, j minus 1. So it's the same as with calculating longest common subsequence. So we can do this here. Okay. So that was it. Okay, so we have, I think, 3 more problems from the previous contest, and I will give some hints for 2 of them. So for Postmen and Pizzerias. So both of these tasks were quite tricky, and I think you need some more, so at least some theory from to get them right. So actually, instead of solving them today, we will solve somewhat easier problem, and then we will see how to extend the solution for this problem to those ones. Okay, so we will have a tree. So let's say that we have a rooted tree, and each of the nodes of the tree has some weight. So each node has weight, and we want to select some of the nodes of the tree in such a way that we will select the root, and we will select some continuous part of the tree in such a way that we want to maximize the sum of the weights of the selected nodes. But so of course we can. So let's assume that these weights are positive, so we could get the whole tree. But there's one restriction: we cannot take more than, let's say, p nodes. So we can select as at most p nodes. The region we are selecting must be connected, and we have to select root, and we want the weight of the selected area to be as big as possible. So how can we do this? So let's again write an image for the dynamic programming on our trees. So we have the root, and we have some children of the root. So first of all, we need to take a root in our area, and then we will have to take some of the nodes here. So we will have we will extend some area here, possibly some of the nodes here, but maybe no nodes, and some nodes here, and again. So we know that in the whole tree we have let's say we have exactly p nodes. So we want to partition those nodes we can use. So we want to partition this p into those subtrees. So let's assume that we can that in our dynamic programming we will calculate the as following array. So we will calculate the array d, which takes the vertex, and also it will take the number of the nodes we can use. So this k will be from 0 to to P. Actually, the P can be as big as n, so let's assume that we can go here from 0 to n. So this is the maximum weight from subtree V using no more than, well, actually we can use exactly k nodes, using exactly k nodes. So we have to take the root if k is greater than 0, and then we have to select some of the nodes. Okay, so if we want to so let's assume we want to calculate the key based on values we calculated in the children. So let's say we want to calculate let's calculate this for the smaller values of k. So what is d0? Well, we have no nodes, so obviously it's 0. If we have d1, then we have to take the root, so it's the weight of the root. So what if we can take 2 nodes? So first of all, we have to take the root, and then we have to take the maximum value from the subtrees which uses on exactly one node. So that would be the maximum of all of the children using one node. Okay, so what's if we take 3 here? So these sums will get complicated. First of all, we have to take the root, and then we either have to put 2 nodes in one of the subtrees, or we can put one node in one subtree and another node in other subtree. So if k gets bigger, these sums get complicated. Well, maybe it's not very important that they are complicated, but as we can see, they are longer. So it will take longer time to actually calculate them. So it's not very, so this approach is not very visible here, but we see what we are aiming at. So actually, what is the problem here? The main problem. So if the tree was binary, so each of the nodes has 2 children, then these sums would be quite easy. Yes, because if we have k nodes to distribute, we have only 2 trees to distribute. So in one of the trees we can put, let's say, L nodes, and in the other tree we will put the another nodes. So k minus 1 because we have the root, and minus L. So these sums would get easier. So actually what we can do is we will be adding all these 3 one by one. And we will be creating somehow the virtual trees, which will contain all the information for us. So let's make a picture. Okay, so let's assume that we have the vertex V, and we have subtree 0, 1, 2, okay, up to, let's say up to I minus 1, and then we have some more subtrees. So we want to add these subtrees one by one, and we will store the information after adding some of the trees. We'll store information in additional array. So let's call it array D. Let me take my Okay, dik. So array small d is the global array, and this array big D will be used only when calculating the children of the specific node. So I will go from 0 to n minus 1. So actually this guy is called n minus 1. And k will be the number of nodes we will have, so it will go from 0 to n. And so this is the maximum weight we can get from subtrees u0 through ui minus 1. Using exactly k nodes. I minus 1. So actually, no, 2. So this guy will be stored in the array d I minus 1 and some value of k. Okay, so first of all, we will be adding trees y by 1. So let's assume for a start that we are calculating d0. So we're calculating the first subtree. So d0 for nk. So we want to calculate the maximum weight from subtree u0, so only from this subtree, using exactly k nodes. So this is easy, because it talks only about this subtree, and we can take this from the lowercase d array. So it's lowercase d from the node u0, using exactly k nodes. So the initialization is easy. Okay, so what can we do in the general case? So in the general case, we have we want to maximal weight from subtrees from u0 to ui, and actually we will be using information stored in this array, d I minus 1. So we have k nodes, and we want to distribute those nodes between this new tree and this pack of trees. So let's assume that this pack of trees will get L nodes. So we want to get a maximum for value L, and this value L goes from 0 to k. So we want to put L nodes in all of these trees, and the remaining ones in this tree. So what do we get? So if we put L nodes here, we get the maximum weight here of value capital D I minus 1L. And if we put the remaining K minus L nodes here, we get this weight. So actually, if we can sum these weights up, and we can take the maximum from all the partitions. Okay. So we know how to calculate all these values d, and now we want to based on So after we calculate this d for all of the subtrees, we want to calculate the value of small d for the root. So it would. So it's again quite easy. So for the, if in the root we can use exactly k nodes. So we first of all have to select the root. So this is the way we get from selecting the root, and for all of the other subtrees, we can use k-1 nodes. So all of the rest of the nodes will distribute in the subtree, and this array d n-1 holds the distribution, the optimal distribution for all of the subtrees. Yeah, so actually, this is the end of the algorithm. So let's see. Where is our answer? So the answer is the value of d in the root, and we have exactly p nodes. Okay. So now let's take a look at what is the time complexity of our solution. So what we are doing here in every node. So let's say we are calculating things for node v, and what is the time to actually calculate it? So yes, so we want to calculate all of these arrays. What is the dimensions of array d? First of all, we have m, the number of subtrees, and then we have the other dimension is n, because we can put here from 0 to n nodes, so it's n. And for each cell in the array, we have a loop from 0 to k, so it's another. So we can just put another n here. So this is the sum for one node. For one node which have n children. And if we want to sum it over all nodes, the sum of the children will be n. So the total complexity is n cubed. Okay, but we can do better here. So actually, we were quite generous in our arrays, because we said, okay, so we can put as much as n nodes in all of the subtrees, but it's not true. Yes. So for instance, let's say that this is the tree, the whole tree, and actually we can put the n nodes in the whole tree. But these subtrees are smaller, yes. So they will have smaller number of nodes. So actually, we don't need to put like n nodes here, because we even don't have the space here. So actually, what we can consider is to put as much as the number of nodes as the size of this subtree. Yes. So in our arrays, for instance, in this array, we do not have to go from 0 to n. We have to go from 0 to size of the subtree rooted in V. And for these arrays also. So for instance, here we do not have to go from 0 to n, but we have to go here from 0 to actually the sum of the sizes of the subtrees we have. So let's try and So let's try the exactly same algorithm, but be more precise in seeing what how many nodes actually we need to store in this arrays. Yeah. So first of all, for RID, if we have a node V, the value of k would go from 0 to SV. So let's say that SV is the size of subtree V. And similarly, if we have RID I, so actually D will not be a rectangular array. Every row of D will have the different length. So if we have DIK, so this will go from 0 to to SU0 through some SU I minus 1. Because this is the sum of all of the subtrees which are in this tree. So these are the sizes of the arrays, and the one thing which we will have to be care about mostly is this loop, because here we go from 0 to k. So we are just putting from 0 to k nodes, but it's not always possible to do this, because suppose that we have a tree, and here we have a place for 2 nodes, here we have a place for 2 nodes, and we want to put 3 nodes in both of the subtrees. So if we want to put 3 nodes, we have to put 1 node here and 2 nodes here, or 2 nodes here and 1 node here. So we don't even can start from 0. So we will write it more. So if we want to calculate from this thing, so we need to. Okay, so first of all, L must go from 0 to k, but also we have another restrictions that L must be no bigger than that the size of this I trees, and also k minus L must be no bigger than the other side. And then we have the exactly same thing here. The exactly same reference. Okay, so now let's. So this is the pretty much the same algorithm, but now we will be more careful in calculating how much time we need to calculate all of these arrays. So now it's time for some math. So let's calculate how much time we need to generate DA. So let's assume that to generate the one row of DA is it takes us time Ti. So what is the time to generate the first row? So in the first row, we are going through 0 to the size of the first tree. So we need to consider size of tree U0 plus 1, because we can go from 0 to the size. So this is the time. And now, more tricky part is exactly calculate how to do this recurrence here. So let's assume that we have two trees. So one of the trees has the size of this size, the sum, and the other one has this size. So let's say that A is the minimum of these sizes and B is the maximum of these sizes. Because some tree will have the bigger size than the other tree. So let's say we have like here A and here we have B. And how much? We will? How many nodes can we put into these trees? So we can put as much as A plus B nodes. So let's take a sum from. I'm taking this straight. Yeah. So we'll be summing from. From 0 to A plus B, because this is as much as nodes as we can put in those trees. Okay. Okay, so I get exactly. Okay, so this will finish. Okay, so we are calculating the ith row of the array D. So we are calculating all the values for different K's. So how many different values of K's we have? We have K from 0 to A plus B. Okay, and now we want to calculate how many values L in this max we will have to iterate through to get our answer. So we are just putting, starting from 0, we are just putting more and more nodes in the trees. So for instance, if we put like if we put one node, we can just put it either here or two. Here, if we put two nodes, we can put all of them here and some of them there. And as long as we so A was so as long as there is less. As long as there is less than B nodes, we can put some of them in this subtree and some of them in this subtree. So actually we can write the formula as follows. We can get. So we are just writing the. So in order to satisfy all the requirements, we will have 1 plus K, 1 plus B, and 1 plus A plus B minus B. Okay, so let's go and try to unwind it. So for K equals 0, of course it's 0. Then we can go through up to B. So for 1 we have 1 possibility, then we have 2 possibilities, and up to b we have b possibilities. Also, if we have a plus b nodes, so we have total nodes, then we have only one possibility to go through them. Yes. So also when n is b, when k equals to a plus b, we have only one possibility to put all the a plus b nodes here. If k is equal to a plus b minus 1, we can have 2 possibilities, because we can be minus 1 here or here. And again, we can have b possibilities. And what about in the middle? If we have at least b nodes, or we have less than b nodes, so then we have b minus 1 possibilities. B plus 1. So again, we have b plus 1 possibilities for all of the different cases. So here we have b cases, here we have b cases, and we have a plus b plus 1. So it's a plus b plus 1 minus 2b. Yes. Yeah. So we can sum it up. So from these two guys, we have b plus 1 times b divided by 2, but these are 2 guys, so and we're just rewriting this thing. So in the end, we will get b plus 1, and this guy will get this guy, so it's b plus 1 times a plus 1. So actually, this is the time to calculate the ETH row. So it's nice that we got the this part, yes? Which one?
I see total.
All right. So we have, yeah. So we can just write it up. It's symmetrical in terms of b and a, so it doesn't matter which is min, which is max. And it just equals to 1 plus sum of I plus times 1 and sum of u0 through su. We just put a and b here. It doesn't matter which is max, which is min. Okay. So this was time to generate the array one of the row, and now we want to calculate what is the time to generate all of these arrays for the whole for one subtree. Okay, so let me just use this. Okay, so let's say that that the time generate the to generate di with all subtrees. So here we generated the DI for this part, but we want to generate DI and all of the arrays D which are in the subtrees. So let's say that this will take us time big TI, and let's assume what we would like to prove by induction is this TI is less than square of the size of the tree, well, minus size of the tree. So we are seeing here that we will go for the quadratic time, not for the cubic time. Okay, so let's say that we want to calculate this for root I, for some root, and how much time will take it. So first of all, yeah, so these are kind of these things I use are kind of confusing. Yeah, so actually what we are doing here, we want to generate all of the RID with all of the subtrees, and let's call it TV. So we are calculating this for the certain vertex. Yeah. So let's call it TV. Okay. So now we first of all we have to generate all the arrays for the smaller subtrees. So for the smaller subtrees, we will have to generate all the TUI for all the subtrees going through from I goes from 0 to n. And then additionally, we want to generate big arrays D, which goes for these subtrees. So we actually calculated how to generate the ith row of this array, and this is TI. So we just have to TI. So this part is to generate everything for all of the subtrees. And this part is to calculate the big array D for all of the bigger packs of subtrees. So actually, this is all of the information which we have to generate for this subtree. So if we prove that this time to generate everything for this tree of size SV is smaller than SV squared, then to generate everything for the root of the tree, when the tree has size n, will get us the algorithm of times n squared. So recall that our total time was n to the power of 3, and we can, so if we prove this, we can get to n power of 2. So it's a quite improvement, which is done not by like rewriting the whole algorithm, but just by carefully analyzing what we really have to calculate. Okay, so now we have to do some math here. Okay, so first of all, we need to use the hypothesis. So we are again summing by I, and these guys are apparently should take no more than this time. So the size of this tree is this, and then we have to add this part, and this part is written down here. So we need to add 1 plus size of ui times 1 plus size of u0 going through size of ui minus 1. Okay, so this is the sum we want to get. And yeah, so we have to be a little bit careful here. Okay. So first of all, get these squares. So we have SUI squared. Then we want to get this guy. So this guy is the. So actually, this is the sum of all the subtrees of D. So it's the sum of all of subtrees is almost the sum of the tree. So actually it's sum of the tree plus minus 1. Yes? This part corresponds to this part. So we are not summing more. And all of these sums correspond to this part. Okay. And now we want to get rid of this part. So let us see what is happening down there. First of all, we have the sum for every I smaller than j. We will take SUI and all of these smaller parts. So we have to take SUI and multiply it by all of the smaller parts. And what we are left with. And yeah. And moreover, we have to calculate 1 times all of these guys and 1 times all of these guys. So S minus 1, like all of these guys, is again S. Oh, let me just, because we should get it right. So maybe we can get what we are driving here. So we should get that this thing is less than the sum of the tree squared. So the sum of 3 squared is s is 1 plus s u0 plus 1 plus s ui. Yes? And squared. So actually, and minus sv, but this part will go from this guy. So if we want to get this correct, we will have to get all these squares here. So these squares, we have them here, and again, all of the pairs. So I think we are missing here some pairs, unfortunately. No, we are. Oh, come on. We're actually not missing anything. So, but because we don't have to prove that this is equal. Yes. So this has to be less than this. Okay. So that was my confusion. So actually, we can prove that this is smaller than 2 times these guys. Yes. So yeah. So again, 2. Yeah. So let's take again what we have. So we have all these pairs. We have 1, and we have 1 times. We have 1 times 1. So let's make it. Okay. Okay, so here we are assuming for all the i's and for all the j's. So this guy comes from here, and this j comes from here. And here we are assuming from all of these ones here, and this guy comes from here. And so yeah, so this will be smaller than, so this is equal, this will be smaller than squared minus s1 minus 1, and 2, because this guy is at most, well, all of the sizes are at least 1, so this is the, so we can just take 2 here. And we only have to consider this 1 times all of these guys here. But so here we have to put like sum of all of these guys. But once again, this is smaller than 2 times. No, actually, we do not have to do this. Okay, so smaller than 2 times these. So let's take a look whether we get it right. So here we have all the squares. Here we have all the pairs which do not take 1. And and here we have all the pairs which takes 1 and 1 of the sum, and we will have here also 1. So yeah, but we have this one here. So we also additionally we have this one here. So I think it could be, yeah, maybe we get some +1 -1 wrong, but in overall this is the idea we can get here. Okay, so sorry that this was more like messy stuff, but maybe if you are close to the Blackboard, you get this I's and J's, a little bit confusing. But overall, this shows us that the time complexity of this whole algorithm is n squared. So yeah. So actually, both of the tasks which were at yesterday's contest, they need this technique to get them in the time limit, and they both use the technique that we are calculating dynamic programming on a tree, and we want to distribute some nodes in the subtree. So the first the first tricky part in both of the tasks is to actually see what are the things we can distribute. Yes, because one of the tasks, for instance, talked about 2 postmen, which has the paths through the trees, and the first thing is actually what is the nodes we are distributing through the trees for this postman. And the task about Pizzerias also had the same thing. So I will leave it right here for the moment, and we will get back for this task, I think, in the next lecture. And so now you can like think for yourself a little bit more on the task, and then I will give some more hints. Okay, so sorry for the long lecture today, and yeah, so good luck with the contest. Today is the team contest like yesterday. The tasks will be from the actual contest we had previous year in Poland. So there will be some more easy tasks in the second than in the first.